In this video, we're going to be looking at a practice exam. So these questions, you could, see some like this on your next exam, but this doesn't, it's not all inclusive. We could see other things on the next exam. But this will be some good practice for us. So let's look at problem number 1. Using your calculator, find the limit for the limit of sine of x divided by x as x approaches 0. Let's look at the graph of the sine of x divided by x. If we did the analysis here, we could look at the one-sided limits because we're trying to find this limit and we're going to use the one-sided limit. So we're going to be looking at the limit of the sine of x divided by x as x approaches 0 from the right. So as x approaches 0 from the right, we're looking at the y values. What are they approaching? And they are approaching 1. And now let's look at the limit of the sine of x divided by x as x approaches 0 from the left. So as our x values approach 0 from the left, we're looking at the corresponding y values. And it doesn't matter that this function is not defined at 0. We can see there's an open circle there, but that doesn't matter. So our conclusion, since the one-sided limits equal the limit of the sine of x divided by x as x approaches 0 equals 1. So on a test, I would like you to draw the graph and show the analysis that you're using to find the limit. Okay, problem number 2. The limit of 6 raised to the x minus 2 raised to the x divided by x as x approaches 0. So we're going to look at our graph. And let's do the analysis on this graph. Again, we're going to use our one-sided limits. The limit, and I'm just going to call it f of x, our function that we're looking for the limit, as x approaches 0 from the right. So as our values get closer and closer to 0 from the right, our y values are approaching. Now this looks like it's above 1 just a little bit. And let's use the trace feature and see. Oh, I'm unable to use the trace feature. We're going to estimate right now. Then we'll look at the trace feature and get a more accurate answer. But for right now, I'm going to say around 1.1. Then we're going to take a look at the limit of this function as x approaches 0 from the left. So as the x values approach 0 from the left, we're looking at the y values, and it's approaching that same 1.1. So our conclusion would be the limit of this function as x approaches 0 equals 1.1. Now let's undo this so we can trace that and see what the value is approaching here. I think we have a tracer here. So here, as we get closer and closer, 1.05, 1.07, and see there's the hole. Now it is telling us that it is 1.1 right there, but it is not defined there. So 1.1 would be our conclusion. Now I would like to show you on the test. I've been very unorganized in my work. So if on the test we would be very organized and we would draw our graph and We would put the graph here, and then we would write our limits. And again, I'm just going to use f of x as x approaches 0 from the right. We would show the limit of f of x as x approaches 0 from the left. And then our conclusion was the limit of f of x as x approaches 0, we concluded is 1.1. That would be our solution. So I'd really like to have the work organized so it's easy to follow. Okay, let's move to problems number 3 and 4. It says determine the limits analytically for problems 3 through 5. So problem number 3. It appears that we're going to use the conjugate. So let me start over here, and hopefully I have enough room. This write's a little big, but we'll give it a try. The limit of the square root of x plus 2 minus the square root of 2x divided by x squared minus 2x as x approaches 2. Now if we use direct substitution, we can see we would get 0 over 0. So the strategy I'm going to use here is I'm going to try to multiply by the conjugate. Let's see if that works. Now when we multiply these together, we would have the first being multiplied together, x plus 2. The middle terms are going to cancel, and we'd have minus 2x, all divided by, and we'd have x squared minus 2x times this quantity. And let's simplify that. Notice in the numerator we have an x minus 2x, so we'd have a negative x plus 2. And in the denominator, I can see that if I factor the first quantity, I would get this, and that appears it's going to be helpful when we continue on. I forgot my... Now I recognize that this quantity here and the quantity in the numerator are the same except they're opposite signs, so that tells me I could pull out a negative and then we would have the same quantity. So this would be the limit, and I could write this as 2 minus x all divided by x. Now when I factor out a negative from that quantity, it would be 2 minus x also. So we would have and then we can reduce these. And I am going to have to go into this area here. So the limit of, and I'm going to pull the negative from the denominator up into the numerator. We don't have to, but we can. Now it appears we can use direct substitution. So if we use direct substitution, we would have negative 1. So 2 times the square root of 4 plus 2 times 2 would be the square root of 4. So we have negative 1, 2 times 2 square roots of 4. But we know the square root of 4 is 2, so we get negative 1 all over 8. So let me get rid of all of that so we can look at the next problem. Okay, number 4. We have If we use direct substitution, we would get -5 all over -1 squared is 1. This would be +3 minus 4. So we get -5, and we get 0 in the denominator. Oops. Now that would tell us that we get -5 over 0. So this limit does not exist because we're getting -5 over 0. So this does not exist. Now, if we were tempted to factor this, is this factorable? Can we say t minus 4, t plus 1? As t approaches -1. And even here, we didn't get our 0 over 0, so it's not the indeterminate form, but here we would still have 1 all over t plus 1, and as t goes to -1, we get 1 over 0. And if we wanted to write the informational limit, you could look at the graph of 1 over t plus 1 and then write the informational limit. Problem number 5. If we use direct substitution, we would get 1 squared minus 1, 0 over 0. So it's the indeterminate form. So let's expand the 1 plus h, 1 plus 2h plus h squared minus 1 all over h. And then the 1's cancel. And we can factor out an h and reduce it in the denominator. Now we can use direct substitution. We get 2. Now find the limit using any method for number 6. Let's go to the graph. So if we looked at the graph, let's trace, we're trying to find as x approaches, it says pi by 2, which is approximately 1.57. So down here you can see it gives us the x and the y value. So I'm trying to get my x value to be around 1.57. It's 1.56, 1.57. It approximately equals 0.63. And it does appear that it is approaching 0.63 from the left and from the right side of pi by 2. So our conclusion would be 0.63. We could do this numerically from the table of values, or we could do it, with the trace function on your calculator like I just did. Find the one-sided limits using any method. Now if we used, for number 7, so first thing, we would use direct substitution, and we would get -6 over 0. So if we looked at this graphically, we could, this says using any method, so, graphically would make sense. But if we're approaching 6 from the left, we're going to have, I'm sorry, we're approaching -6 from the right, it appears. So if we're approaching -6 from the right, we're looking at values like -5. If we looked at -5, we would have -5 all over 1. Now if we looked at -5.5, we'd have -5.5 all over, we would have 1/2. So we would invert and multiply. So this would give us a negative maybe 11. And if we continued this process, getting closer and closer to -6 from the right, these numbers appear that they're going to be getting larger and larger and larger in the negative direction. So we could conclude that the limit as x approaches -6 from the right, the informational limit, -infinity. Number 8, if we looked at this one graphically, we could, let's see, if we use direct substitution, do we get 0 over 0? So let's look at this one graphically. So plugging in our y equals the square root of x squared minus 9 divided by 2x minus 6. And let's graph that, see what it looks like. And we're looking as x approaches 3 from the left. Now notice the graph. From -3 to +3, it doesn't appear that there are any values. It's not defined. So let's look back at this graph. Do you see if we plugged in 0, we'd get a -9 under the square root. It's undefined. If we plugged in 1 or 2, it's still going to give us a negative value. So this is not defined when x approaches 3 from the left. So the only thing that we could write for this one is that this one does not exist. So number 8, we would write does not exist. And we interpret this one graphically. We couldn't write any informational limit. Now, if it would have said as x approaches 3 from the right, we could have written an informational limit, looked like infinity. Number 9. Now, if we looked at the sine graph, we know the sine graph just oscillates like this. And we know the idea behind the limit, as x gets larger and larger and larger, what y values are we approaching? Well, we're not approaching any y values. This is just oscillating. It's not approaching any y value. Now, the y values are oscillating between -1 and 1. Those are not going off to infinity. So the only thing that we can write for this one is it does not exist. Okay? And so this one up back here up at number 8, we should have the graph that we saw. You need to draw in that graph. And this one, you could give it a little explanation like I just did. You could say that the sign is oscillating between -1 and 1. The y values are not approaching any value, therefore it does not exist. Number 10, we have the limit of the absolute value of x minus 8 divided by x minus 8. If we looked at this graph at 8, we would see that the graph looks something like this. So if we looked at this graphically, we could say, well, this limit is looking for the value as x approaches 8 from the right, which would be +1. So this said we could do it any way we wanted. Now if you wanted to build a piecewise function for this, that would have been fine also. You could have said x minus 8 over x minus 8 when x is greater than 8, and then negative x minus 8 all over x minus 8. And if we're approaching 8 from the right, we would use this one here, and you can see that is just equivalent to 1. Okay, the following problem is find the vertical and horizontal asymptotes of the graph, and I think it said analytically. So we have to show this analytically using limits for possible horizontal asymptotes. Now when we're checking for horizontal asymptotes, we have to show as x is going to positive infinity and negative infinity. So this might take a little bit of room, but we need to find the limit as x approaches infinity of the square root of 2x squared plus 1 divided by 3x minus 5. Now when we're working with an infinite limit here, we know that we can divide by the highest power of the denominator. So we would divide everything by x. So if we divided everything by x, the numerator and the denominator, now to get that x up under the square root, we're going to change it to the square root of x squared. And I'm just going to go ahead and divide 3x by x and 5 by x. Now we would have the limit. I've gotten that 2x squared plus 1. I've gotten that up underneath the and so if we divided under the square root, we'd have 2 plus 1 all over x squared divided by 3 minus 5 over x as x approaches infinity. And we can take that limit up underneath the square root, and we know this would go to 0 when we analyze that. The limit of 2 as x goes to infinity is just 2. And we know this goes to 0, so we would have square root of 2 over 3. Now we do have to check negative infinity also. Now the only difference here would be at this step, remember that for this step right here, we would divide by a negative square root of x squared, because the square root of x squared, the definition is it's the absolute value of x. So if we're going off to negative infinity, that's going to force the values to be positive, but we want them to stay negative. So at that point, we would just divide by the negative square root of x squared. And then everything else would be the same, and we would have negative square root of 2 plus 1 over x squared, and then 3 minus 5 over x. And this would go to 0, this would go to 0, so we would have a horizontal asymptote at y equals negative square root of 2 over 3. So we would note that we have a horizontal asymptote here, and we have a horizontal asymptote here. For number 11, I don't know if I'm going to have to erase all of this, we would take the limit, and then we would divide by the highest power of the denominator. So we're going to divide everything in the numerator by x squared and everything in the denominator by x squared. So I'm just going to do that in one step. So we'd get 3 minus 1 over x minus 2 over x squared. And then we'd have 5 plus 4 over x plus 1 all over x squared as x goes to infinity. And we can take the limit term by term, and we know these go to 0. Therefore, we're left with 3/5. And we'd also have to check negative infinity. But the process would still be exactly the same. All over 5 plus 4 over x plus. Now, as x goes to negative infinity, this still goes to 0. This still goes to 0. Goes to 0. Goes to 0. So we get 3/5. So we have a horizontal asymptote at 3/5. And here we're now for number 10, if we wanted to find the vertical asymptotes, I'm going to have to erase a little bit here. If we wanted to find the vertical asymptotes, we know to find the vertical asymptotes we would set the denominator equal to 0. So if we set the denominator equal to 0, we would have 3x minus 5 equals 0. So x would equal 5/3. And there's where we would have a vertical asymptote. And on number 11, you could graph that to see if it ever equals 0, but since it's all plus signs there, it appears that that would never equal 0. So it doesn't appear that those, for g of x, that doesn't appear it's going to have any vertical asymptotes. Find the slope of the tangent line to the curve at y equals 9 minus x squared. We know to find the slope of the tangent line, we would use our limit. So we would have the limit of f of x plus h minus our f of x all divided by h as h goes to 0. Now if you put in f of a plus h minus f of a, that's fine because we're trying to find the slope of the tangent line at x equals 2 only. This would equal the limit, and this is finding our f prime of x, and then we can just plug in 2 for x. So we would have the limit of 9 minus x plus h squared minus 9 minus 2x. I missed our x. And that would all be divided by h. And then if we expanded this out, and I don't have a lot of room for this one, so let's see if I can fit it in here. The limit of 9 minus, now this is just going to be x squared plus 2 plus 2xh plus h squared. So it'd be minus x squared minus 2xh minus h squared. Then we'd have our minus 9 plus 2x squared. This is getting away from me here. All over h as h goes to 0. Now let's look at our like terms. So what do we have left? We have the limit of, looks like x squared minus 2xh minus h squared all over h. Now it appears that I've made an error rushing through this. So let's see, what did I do? 9 minus x plus h squared minus 9 minus 2. Oh, I see where it is. See, I was rushing through this and I forgot my 2. So right here, I forgot the 2. So if we went back and put that 2 in, we would have 2 here. And I'm sorry about this. Let me erase this. This would be 4. And I'd have to squeeze in another 2h squared here. So this would be 4, and this would be 2h squared. Okay, so our negative 2x squared, 9, negative 9. So what we have left is this. Now we can factor out an h. 2x minus h all over h as h goes to 0. We can reduce, and direct substitution gives us 2x. So if we want to find the slope of the tangent line, and I failed to change this along the way, so this would be negative 4, and so this would be negative 4x. Yep, let me clean that up. So this would be negative 4x. So if we plugged in x equals 2, we would get the slope of the tangent line. So that would be negative 8 would be the slope of our tangent line. So we would have, it says find the equation of the tangent line. So we plugged in our slope. Now this is, I'm kind of glad I did that. This is a mistake sometimes that I see, is the slope of the line is negative 8, not negative 4x. So the slope of the line is negative 8. And then we can use our value of x and y that we have up here to plug in to find our b. So y would be 1 times, we have negative 8 times 2 plus b. So b plus a negative 16 equals 1. So we would add 16 to both sides, and we get our y-intercept. So we have the equation of our line plus 17. So that's the equation. A ball is dropped from a 240-foot building, and the position of the ball can be modeled by the equation negative 16t squared plus 240. Answer the following questions. How high was the ball 3 seconds after it was dropped? Well, this is telling us the position of the ball is right here. So if we plugged in 3, we would have h of 3 equals negative 16 times 3 squared plus 240. So we have negative 48 plus 240. So that looks like it's 196 feet. What was the velocity at 2 seconds? Now to find the velocity, we need the derivative. We need h prime of t. Now you would need to go through the limit process and find the derivative. So go through this process and find the derivative of this function. Now when you found the derivative, you would see you get negative 32t. So you need to go through that process though of finding this on your own, and then we're trying to find h prime of 2. So here's our h prime of t, so we're going to plug in 2. So negative 32 times 2, and that's negative 64, and our units would be, let's see, the original problem gave us our units, I believe. It says 240-foot building, so it would be feet per second. Part C, how fast was the ball traveling when it hit the ground? Now, when the ball hits the ground, the height is 0. So we would have 0 equals negative 16t squared plus 240. We set our position function equal to 0. So this would give us t squared equals 240 divided by 16. So that is 15. So t, we don't need the negative value. We just take the positive because this is time. So that's approximately, and it's just a little bit under 4 seconds. So how fast was the ball? Now this is when the ball hit the ground at about 4 seconds. Now to find the velocity when it hit the ground at that instant, we go back to our velocity function. So we'd be looking for h prime of the square root of 15. See, we're going back up here to our velocity function. So negative 32 times the square root of 15. And that would be in seconds. And I believe that's approximately 123.93 feet per second. So that's feet per second. Find the limits. Find the limit of the following if it exists. Now this one, the limit of f of x as x approaches 5. I'm going to draw a sketch of the graph just to get a feel for this. I know 3x squared minus 1 is a parabola. It looks like this, something like this. But this is not defined at 5 on the parabola. Let's say this is 5 here. It says that when x equals 5, the function equals pi. So I know that if the function was defined at the parabola at 5, that would be something like 74. So it's defined down here at pi. Okay? So we would have an open circle up here in the graph at 5. I know that's kind of big, but okay, whoops, went through it. Okay, so that's the idea. Now let's look at our limits. The limit of f of x as x approaches 5. Well, as x approaches 5 from the left, we're approaching this value here. As x approaches 5 from the right, we're approaching this value here. So we don't want to take where it's defined here at pi, and we want to take it up here, and I think I said it was 74. So this would equal 74. Now the next one says the limit of f of x as x approaches pi. Now don't be confused on this one here, because if now our x value, we're going to be looking at approaching pi from the right and pi from the left. So we'd be using our function to find out, well, what are the y values approaching as x approaches 5? So if we just plugged in pi for x, this would be the exact value of this limit. It'd be 3 times pi squared minus 1. And if you wanted to use a decimal approximation for your answer, just write the decimal approximation with the about equal to sign. Number 15, sketch the graph of the derivative on the same graph. This particular graph, we did sketch that in one of our lessons, so we're not going to go over this. You can go back and look at the previous, I believe it's in section 1.9. We graphed the derivative graph, and it looked something like this. So make sure you're comfortable graphing the derivative function given some function. (16) Show that the function is continuous show that the function above is continuous at x equals 1. So let's make sure we can see the graph. Now, if we're going to show a function is continuous at a point, we have to use the 3 criteria. Those 3 criteria. First is f of 1 defined. Well, looking at this function, it is defined when x equals 1 and it equals 1. Second, we have to show that the limit of f of x as x approaches 1 exists. Looking at the graph, as x approaches 1 from the right, we're approaching that value. As x approaches 1 from the left, we're looking at the y values, and it's approaching 1 also. Now the last criteria is we need to show that f of 1, does that equal the limit of f of x as x approaches 1? And if we go back to criteria 1 and 2, we can see those are equal. So all three criteria are satisfied. So this is continuous at x equals 1. Number 17. Discuss the continuity of this function. This is a composite function. If we looked at x squared minus 4, this is continuous on its domain because it's a polynomial. So we would write this is a polynomial, so therefore it is continuous on its domain. The square root is a square root function is continuous on its domain. So if we compose a continuous function into another continuous function, it will also be continuous. Now we do need to look at the domains here. Now we know the square root function, x has to be greater than or equal to 0. So if we looked at x squared minus 4 greater than or equal to 0, I would look at factoring this x minus 2, x plus 2 greater than or equal to 0, and then I would just do some analysis on those factors. Where is x minus 2? Where does that change from positive to negative? Well, that changes at 2, and x plus 2 changes at negative 2. Now, in x minus 2, if the values of x are greater than 2, this quantity is positive. If it's less than 2, it's negative. Now for the x plus 2, if we have values of x greater than negative 2, then this quantity is positive, otherwise it's negative. Now I'm going to draw a line at those values and then say, well, if I have a negative quantity times a negative quantity, I get a positive quantity. A negative quantity times a positive quantity will be negative, and a positive quantity times a positive quantity will be positive. And I wanted to know where this is greater than or equal to 0, which means it's positive. So we can see those intervals would be from negative infinity to negative 2, and we can include negative 2, and then we would have 2 to infinity. So that's where x squared minus 4 would give us positive values. Therefore, the square root of x squared minus 4 is continuous on those values. However, we've discussed the continuity, and that discussion was just for the open interval. So we would have to show that at the endpoints, and I believe the graph looks something like this, I'm hoping. So we would need to show at the endpoints the limit of this function as x approaches 2 from the right equals 0, and the limit of f of x as x approaches 2 from the left equals 0. And then go back and use our three criteria at -2 and 2. So if I wanted to show it was continuous at 2, I would first of all show f of 2, that equals 0, the limit of f of x as x approaches 2 from the right equals 0, and f of 2 does equal the limit of f of x as x approaches 2 from the right. Therefore, I can state now that this is continuous on the closed interval. And I would do the same thing with -2, and then after I showed it was continuous at -2, I would then say, yes, we are continuous on those intervals.